Hello everybody, we start our lecture, and today I want to give the first theorem, measurability criteria. And sometimes this is given as a definition. So a subset A of I, let me recall that it's a fixed unit Q. Is Lebesgue or Jordan measurable if and only if for arbitrary epsilon greater than 0, there is an elementary set let me call it with index epsilon such that all the measure Lebesgue or Jordan, depending on what we consider, or the symmetric difference between A and M epsilon is less than. Let me recall that symmetric difference is union of two differences. A minus M epsilon and M epsilon minus. So all together. And so A minus M epsilon is union of two differences. So if we have A and we have M epsilon, something like that, recall M epsilon is an elementary set. It means it consists of several intervals. Like that. See here, polygonal curve is a boundary, the boundary of M epsilon. So, what is symmetric difference? If that is A, right? Our set A, then symmetric difference is this. So, everything what is in precisely one of those sets. Not in both, but precisely in one of those sets. So symmetric difference between them. So you see that this criteria says when we have a measurable set. We have a measurable set if the difference between our set and this, you see, elementary set, so which formed by several intervals. So this symmetric difference is small we want according to the outer measure. And recall that outer measure means that we can cover by sufficiently small amount of intervals. Okay. Proof. We'll start with sufficiency part, which is slightly easier. So, sufficiency. We suppose that for arbitrary epsilon, there exists an epsilon such that the inequality holds. Equality holds. Okay, so we want to prove that A is measurable. Let me recall what is measurable according to our definition. So recall that everything is supposed to be included into our fixed QKI. Everything is inside this Q. Also, we may suppose that our elementary sets are also a part of this Q. Smooth curve. Yeah. So smooth curve is boundary of A. And polygonal curve is boundary of MS. So what is colored, let me say, is precisely this symmetric difference. Okay, so let me recall that we need to prove that what means measurable. Measurable means that if we consider the difference, which is denoted by A prime, so everything outside of A is A prime. What determines the smooth curve be inside or outside polygonal shape? Nothing. We choose a polygonal set M epsilon, somehow doesn't matter how. The only thing which we are interested in is in that the symmetric difference should be small in the sense of the outer measure. Nothing else. Nothing else, that's all. So, A prime and measurability means that the sum of Lebesgue or Jordan outer measures should be equal to 1. 1 is the measure of the whole cube. So, you see, we suppose this condition is satisfied and we want to prove that. So, and okay. How we'll prove it? We'll prove it by covering our set. A by something and also A prime something. And So what is this something? Yeah. So look. Suppose also M epsilon is a subset of AI. This can be achieved just by intersect. So otherwise, suppose we have something outside, then we may forget about it. A is a subset, so the part of M epsilon which is outside of Ki is not important for us, and it has some extra madness, so we don't need to consider it. So M epsilon is a subset of Ki, right? Then so in fact, M epsilon prime equals to S for A, that is difference between AI and M epsilon, right? So then by properties of volume, we have volume of M epsilon plus M epsilon prime is equal to 1. And also, okay, so A is a subset of M epsilon together with A minus M epsilon. Because I added to the set M epsilon everything which was not included into this M epsilon. And difference is a subset of symmetric difference. So I can add more, and then of course we have the inclusion like that. Then look what happens with A prime. So A prime is everything outside of A but inside our cube. And then epsilon prime, analogously, everything what is outside of M epsilon. So let me write down analogous thing for A prime. Right? And then look, what is A prime symmetric difference with M epsilon prime? A prime symmetric difference with M epsilon prime. That's A prime minus M epsilon prime together with M epsilon prime minus A prime. Then look.
Professor.
Yeah. What is the rest of mu A plus mu A prime equals to 1? Nothing. Sorry. Nothing. E is nothing. That is not minus. I couldn't understand. Nothing is here. That is on the blackboard. Okay. That's precisely one. Yeah. So now look what is written here. Difference between A prime and M epsilon prime. So everything what is A prime, but not in M epsilon prime. Now remember, what is M epsilon prime? M epsilon prime is everything what is not in M epsilon. right? So if we are not in M epsilon prime, we are in M epsilon, right? But we are not in A. So it means that this is precisely that one. And on here we have like. So that is precisely symmetric difference. So that is precisely like that. Now, look. I can write the following chain of inequalities and equalities. One is equal to volume of our fixed cube, Ki, right? Then our fixed cube, so we know that our fixed cube is union of two sets. And we had a property of the outer measure. So if that set is covered by union of two sets, then outer measure less or equal than sum of outer measures. Less or equal. So I can write inequality like that. Outer measure. Maybe Jordan or Lebesgue doesn't matter. A plus outer measure of A prime. Yeah. Then, according to those inclusions, I can continue this chain of inequalities by using again same property of outer measure. So for this one, then also for that one, and then to equal measure, outer measures. Same, right? So we have our two outer measures of that symmetric difference. Okay? And then look, elementary set. For elementary sets, outer measure coincides with one. So I can write equals to volume plus volume, and here 2 times outer measure of this symmetric difference. But as we suppose that outer measure is less than epsilon, right? And the sum of volumes is equal to 1. So less than 1 plus 2 epsilon. Now look what we obtain. We have inequality. 1 less or equal than this fixed number, right? Sum of outer measures. Fixed number doesn't depend on any elementary set. Just the sum of outer measures. Less than 1 plus 2 epsilon. For arbitrary epsilon greater than 0. Since this is true for arbitrary epsilon greater than 0, then it follows that the sum of those outer measures is equal to 1. And that is precisely what we wanted to prove, because that is the definition of measurability. So sufficiency part is done. Now let's see. Sorry? Oh, yeah. Thank you. Let's this. Okay. Now We suppose A is measured. Then A prime is also measured. Why? Because according to the definition, look, if I'll take instead of A, I'll consider A prime. Then they interchange, right? And here the same, right? So it means once a set is measurable, then its complement to the cube is automatically measurable as well. Okay. Now, what are outer measures? Let me recall what they are. So, by the definition of the outer measure, for arbitrary epsilon greater than 0, they exist coverings of both A and A prime. So these are elementary sets. Such that two inequalities are valid. So outer measure of A less or equal to the sum of volumes less than outer measure plus epsilon, and analogously similar inequality for A prime. That is by the definition of the outer measure. Because what is outer measure? What is outer measure? That is infimum of all such sums. And what is the difference between Lebesgue and Jordan? The difference is in how many terms. For Jordan, we have finitely many. For Lebesgue, we have infinite. Okay. Now, look at the right-hand side. It means that here we have for Lebesgue measure, by the way, only for Lebesgue. For Jordan, such problem doesn't appear because we have finitely many sums, right? And finitely many terms in the sum. Which problem may appear for Lebesgue? We have infinitely many terms. We have a series, right? And series may be divergent. But here not. Why? Because of that inequality, right? So that is a finite. This sum of series is finite. So those series are convergent for Lebesgue case. What I mean by Lebesgue case, because for Jordan, no series. So we don't need to consider such a problem. So for Lebesgue, we have a series, but it is converged for both cases. Okay, but if the series converges, Then what means convergent series? It means that partial sums converge to the sum. Partial sum converges, then the remainder tends to 0. The remainder. So the whole sum contains first terms partial sums, right? And the rest remainder. So remainder tends to 0. Hence, for this epsilon, there exists a number, let's say capital L, such that sum for L from L plus 1 up to infinity of L less than epsilon, and I don't want to introduce two different numbers, so remainders will start from the same number, right? Okay, then look, what happens? So remainders of those two series are sufficiently small. So denote by M epsilon the union of the first L sets PL. So then what happens? Yeah, in fact, maybe I want to formulate a claim. So claim is that, in fact, this is precisely the elementary set which we want to construct. So claim is that the Lebesgue measure, and of course Jordan measure, will satisfy the same inequality as well. In fact, even less. It will be less than 6x. Okay, that is our equation. And let me start with this claim. So now, okay, what is symmetric difference? A symmetric difference with M epsilon is by definition A minus M epsilon together with M epsilon minus A. Union of two differences in different orders. Now, you will see why 6 later. Yeah, that's because of the proof. Yeah. So, look, the first part is easier. Why? Because, remember, yeah, I forget to mention it here. The main property of those covariants, I said these are covariants. What means covariants? A is a subset of the union, and A prime is a subset of the union of. So according to the definition of outer measure is infimum of those sums over all such covariants. Okay, so what is A minus M epsilon? A minus M epsilon. So look, A was covered by the union of all those things, right? And then we included the first capital L into M epsilon, right? Then what is not covered by M epsilon? only union of the rest, right? Hence, outer measure is less or equal than sum of outer measures, and outer measures here coincide with this. Yeah, in fact, here I could refer to the definition of the outer measure. Lebesgue outer measure. It's important. And that is less than x, right? So, once again, that is for Lebesgue. And for Jordan case, A minus M epsilon is empty. Why? Because we have no series at all for Jordan case. So we don't need to consider any such remainders and so on. So for Jordan case, M epsilon includes the whole sum. Okay. Now, yeah, so you see, outer measure of the first term is less than x. So it means that we have to prove that the rest is less than 5x. And that should be done. That should be done. Yeah. Okay. So now yeah. Okay, where it is better to write? Continue. Yeah, I think I can. How much? Yeah, I think I can use just that one. Yeah, also. Yeah. So, analogously, we have similar thing, but maybe, yeah, also denoted by Q epsilon is union of QL. So we have A prime minus Q epsilon is covered by that one, so we have analogous estimation less than epsilon, that is analogously, and for Jordan we have A prime minus Q epsilon is empty. For Jordan that is empty, for Lebesgue we have that is analogous levels. Yeah, these are two things which are necessary for us. Okay. Yeah. Now I need to consider that difference between M epsilon and A. Yeah. So M epsilon minus A. Intersection. Yeah, I get this. So, M epsilon minus A is a subset of M epsilon intersect with Q epsilon union with what? Q epsilon prime minus A. Yeah, that is very nice idea. Yeah, so look what we have here. Everything in M epsilon which is not in A, right? Then where is it? It is either simultaneously in Q epsilon, right? Then this is in this intersection, or it does not belong to Q epsilon, in Q epsilon prime. But it does not belong to A, right? And then analogously to what I did with A and M epsilon, right? Now I will put prime here, so that is precisely M epsilon intersected with Q epsilon and A prime minus Q epsilon. Then look, this can out measure less than epsilon, right? So we need to prove that that one is less than 4 epsilon, right? But remember, according to properties of elementary sets, we have the following equality. So volume of intersection, roughly speaking, this is like that. So we have one set, another set, right? So volume of intersection, we should take the sum of volumes without volume of the union. Sum of volumes without volume of the union. Right? Because when we add volumes, then we take into account the intersection twice. Once here, and that is second. Yeah, that is okay. Then now look for M epsilon plus Q epsilon. Look, M epsilon plus Q epsilon, that is the sum okay, let's do equal. The sum, maybe they have intersection, doesn't matter, of PL plus the sum of QL by the definition of what was in Q epsilon and P epsilon. Then here I can put even larger sums by infinity. And those infinite sums are less than outer measures, the sum of outer measures. plus 2f, right? And the sum of those two outer measures is equal to 1, since measure our set is matched. Yeah. For Jordan, it's the same, but without that part, right? We don't need to include infinite sum. So we have an estimation 1 plus 2 epsilon, and now I'll prove that that one is greater than 1 minus 2 epsilon. Altogether, 1 plus 2 epsilon minus 1 minus 2 epsilon gives 4 epsilon. That is the plan. Now, to finish the proof, what I need is to observe the following thing. So, the whole cube is a subset of the union of PL together with union of UL. Because, you see, union of PL covers A, union of QL covers its complement. So altogether they cover the union, so they cover Ki. And that can be represented as M epsilon together with Q epsilon, and then union of L plus 1 up to infinity, and union of that one. Hence, by properties of the outer measure, I can write the following chain. So outer measure of Ki, Lebesgue, coincides with its volume, that is 1, less or equal than the sum of outer measures. Plus, sorry, where is chap? Outer measures of those are volume. So L. Yeah, here also outer measure is equal to volume. So less than volume M epsilon union M epsilon Q epsilon plus, and those sums less than epsilon, both. So plus 2 epsilon. And it follows from these inequalities that the volume of the union is greater or equal than 1 minus 2 epsilon. That is precisely what we want. Because, you see, yeah, let me return where is it? Yeah. So M epsilon minus A is a subset of that one. Measure of this term less than epsilon. Measure of this intersection, its volume, equals to that one. The sum of first two terms less or equal than 1 plus 2 epsilon. That one greater or equal than 1 minus 2 epsilon. So altogether, this less or equal 1 plus 2 epsilon minus 1 minus 2 epsilon for epsilon, right? So we have this measure of that one less than 4 epsilon, less than epsilon. So altogether less than 5 epsilon, epsilon, 6 epsilon, right? That is my answer to the question why 6 epsilon. and the theorem is proved, right? So we have found for arbitrary epsilon, we have found elementary set, which is not far from this Lebesgue measurable set. Yeah, for Jordan measure, you see, doesn't appear, right? So we have immediately the sum. Now we have this doesn't appear, so we have immediately the inequality like that. Also, for the rest, you see, yeah, nothing is here, right? So it means that the volume is just greater equals to 1, in fact. But of course, so for Jordan, you don't need to put 6 epsilon, it will be even smaller, but it doesn't, right? So let's now I want to give next definition, and yeah, firstly I will erase that one, and we'll consider so-called algebra of sets. So, what is algebra? In general, usually that is when you can add and multiply. And for sets, analog of addition is union. Analog of multiplication is intersection. That is the explanation of this term, algebra of sets. So I'll use this retainer of measurability and nothing else. So the proof is not anymore. Okay. Picture. Result. Okay. Now, formal definition of algebra of sets. Definition. A collection A of sets is called an algebra of sets if for arbitrary two sets A, B in this collection, their union is in A, intersection is in A, difference and symmetric difference, all of them are in A. And there exists U in A, called universal set or unit, such that for arbitrary A in A intersected with U in A, and A union with U is U. So U is maximum. U is maximum set. And next theorem theorem 2. The collection of all Lebesgue or Jordan measurable subsets of AI form the collections. Yeah, the collections. So we have two collections of all Lebesgue measurable and of all Jordan measurable subsets. Both of them form algebras of sets with U equals to Ki. So the unit is the maximum set, which contains everything. Universe for our theory for a while. So for a while, the universe is this fixed Q. So proof. Yeah, in fact, the best is to use this measurability criteria. So, suppose, yeah, in fact, both proofs, I mean, for Lebesgue and for Jordan are absolutely identical. That is why I will not write J. But it doesn't mean that this theorem is only for Lebesgue. No, it doesn't matter because the proofs are completely identical. So suppose A, B are measured. You see, I omit words Lebesgue or Jordan. Doesn't. Are measured. According to by theorem 1, this theorem, right? For arbitrary epsilon greater than 0, there exist two elementary sets, M epsilon and N epsilon, such that outer measures of symmetric differences are less than epsilon for both of them. Yeah. Then what we'll do? I want to prove that the union is measured, right? And for that reason, I'll consider symmetric difference with the union of n. So the union of two elementary sets is again an elementary set. I want to prove that this symmetric difference is small. What means small? Outer measure is small. Okay, then what is symmetric difference? Firstly, let me write by definition. So I should consider union minus union of M epsilon and epsilon. And yeah, like that. Union with difference in inverse order. Union minus A together with B. Yeah, that's okay. Let's do equal. Now look what I want to do. Here what is written? Difference between this union and that union. So what it means? I should consider everything in that union which is not included into that. That is a subset of what? If I consider everything in A without an epsilon, together with everything in B without an epsilon. Why is that it's true? I mean this. Because look, if we have an element here, then it is either in A, right? Then it should be not in that union. But I consider that should be not in M epsilon. So I don't care about M epsilon. Of course, it means that this set is greater than that one, right? So it means, oh sorry, that one is great, right? That one is greater than this. Because here I consider everything what is not in the union, right? But now it's sufficient to consider everything what is not in one, not in the union. So that is the subset. Obviously for the second, but M epsilon minus A together with N epsilon minus B. Yeah. Then I can unify pairs. That is precisely symmetric difference A with an epsilon, those two, together with symmetric difference. Yeah. Then, by properties of the outer measure less or equal to the sum of outer measures, A symmetric difference with an epsilon plus B symmetric difference with an epsilon, right? And each of them is less than epsilon, so altogether 2 epsilon. It means by theorem 1 implies that A and B is again matched. It's matched. Right? Okay, then for intersection, yeah, we know that A is measurable simultaneously with its complement to the union Q. We know it by the definition, in fact, of the measurability, right? Then, look, what is A intersect B? Yeah, I should consider A prime together with B prime and then take prime. That is by properties of sets. So duality property of union and intersection. So if you have two sets, right, and B, right, then what is intersection? You should take complement to A, complement to B, take the union, right, and then take the complement. It gives precisely the intersection. And you see, measurable, union is measurable, complement is measurable. So intersection is measurable. Yeah. Then A minus B is A intersect with B prime, also measurable. And finally, symmetric difference is union of two differences, right? And of course, U is Ki is always, right? Because everything intersected with Ki is that everything. Okay, next theorem. Next theorem. Theorem 3. Find the activity of measures. Again, here arbitrary measure is considered. So if A1 from A are disjoint Lebesgue or Jordan measurable, then the union, the Lebesgue or Jordan measure of the union equals to the sum of Lebesgue or Jordan measures. So measure of union equals to the sum of measures, of course, for disjoint sets. And proof is again completely analogous for both Lebesgue and Jordan measures. And also, I'll do it only for m equals to 2, because after that we can use induction. So we have two sets, A1 and A2, and apply theorem 1. So, what it means? It means that for arbitrary epsilon greater than 0, there exist elementary sets, let me say I epsilon, elementary, such that yeah, in fact here now I may forget about, no, not yet, because I don't. No, I know it's measurable, so how to measure it coincide with measure. So AI symmetric difference with MI epsilon less than epsilon I1. So we have two measurable sets, and we can find elementary sets. Here I can forget about how to measure, since we know that if it is measurable, then symmetric difference is measurable. Hence, instead of how to measure, we can write measure. Okay. So, let me write then many inclusions. I need many inclusions now. Okay, so in fact, all. I think for all of them, I have a lot. Yeah. For all of them. So MI epsilon is a subset of AI together with MI epsilon minus AI. Analogously, AI is a subset of MI epsilon together with AI minus MI epsilon. Now with unions, the same thing. Yeah, for union, here they are disjoint of course, A1 and A2. I could write here like that. That doesn't matter. So union M1 and M2, union with the difference between A1 and A2 without that union. Yeah, and analogously for M1 together with M2. The subset A1 together with A2 union with M1 union with M2 without that union. Yeah. Here, of course, I equals 1. So we have so many inclusions, right? And after that, yeah, so I'll use properties of the outer mesh. They give, for example, U star of mi epsilon less or equal the sum of U star of ai plus U star of mi epsilon minus ai. And now, remember, elementary, hence I can write here volume less or equal. Here I can write just measure, not outer. And here also measure. Yeah, but in fact, this difference less than symmetric difference, so epsilon. That is I want to. Analogously, for the measure ai, also I from 1 to 2, and ultimately for all others. So measure of the union less or equal than yeah, it is not so easy. Yeah. M1 union with M2 plus, here let me write for a while just measure A1 union with A2 minus M1 union with M2. Yeah. And M1 with M2, let's equal, then measure 1 union with A2 plus measure all that difference M1 with M2 minus M1 with A2. Yeah, now maybe yeah, you see, we considered one such a construction, union without union, right? Union without union. And then we took in pairs, and finally we obtained like that, right? So we see those terms are less than, yeah, we need 2 epsilon, and here also less than 2 epsilon. But altogether, it gives us several inequalities. So look, you see, difference between them, between those two, is less than epsilon in both directions. It means that we obtain the difference between measures and volumes of related mi epsilon is less than epsilon I from 1 to 2. And also difference between measure of the union and volume of the union of those. Oops, epsilon. I forget epsilon. I'm very sorry. I should insert everywhere epsilon. Everywhere should be with epsilon. Everywhere with epsilon. With epsilon. 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 Yeah. Less than 2 epsilon. Yeah, once again. Okay. Now, I think I may refer to what was done before, or no, not yet. Now, I need to, I need to use analogous thing with 6 epsilon. So, let me consider now. So now I want to consider the intersection of those M1 epsilon and M2 epsilon. So M1 epsilon intersection with M2 epsilon. Let's do it. So the intersection is measure of okay. M1 epsilon is included, here, right? So let me write like that. A1 together with M1 epsilon minus A1. The second with analogous in A2 together with M2 epsilon minus A2. Now let's use properties of operations with sets. So look, that is distributive law. You have a sum multiplied by something. So you multiply by each term. Then what we have? We have the following thing. So firstly, I should consider this union. One, intersect with A2. Yes, that one. And then union with same thing, A1 union with M1 epsilon minus A1. Intersected with M2 epsilon minus A2. Okay. One more part. Now look, A1 and A2 are disjoint. Hence, we may forget about this A1. Okay? Yeah. Yeah, and then look. This set is a subset of the very last one. In fact, I may write even symmetric difference, doesn't matter. Because we have intersection of that one with something, right? And that one is a subset of analogously that one. We have intersection with something. And look, measure of each of those symmetric differences is less than epsilon. Hence, altogether, less than 2 epsilon. Yeah, so we see measure of the intersection less than 2 epsilon. Then, look, M1 epsilon together with M2 epsilon, right? That is equals to the sum plus M2 epsilon minus volume of the intersection. We used it once, right? Yeah. Yeah. And yeah, now I think I can here. I should put I have an estimate above. Yeah. I have the estimate. Yeah. Yeah. So what it gives, and we can unify what we obtained up to now. So that is union together with intersection less or equal, yeah, measure of union do I need it? Wait. The measure of the union, I should estimate it. Let me collect them all the time. So measure. Let me write down the rest. So what I so I have measure of the union. Measure of the union. Right? That is less or equal than the sum of outer measures. Outer measure coincide with this sum. The property of outer measure gives that one. That is precisely mu of A1 plus mu of A2. Then that is less or equal than measure of M1 epsilon plus volume, M2 epsilon plus 2 epsilon by those two, right? Those two. Yeah. Then this sum, according to that one, yeah, that one, is less or equal than M1 together with M2 plus, here I have intersection less than 2 epsilon, so altogether 4 epsilon, right? Yes. Yeah, and lastly, what I need, yeah, that one, that one, that one, that is what, yeah, that is less than measure of the union plus altogether 6 epsilon, once again. Yes, yes, yeah. So forget about outer measure, and what we see now, the sum of measures is between measure of this union and measure of this union plus 6 epsilon. Since that is valid for arbitrary epsilon greater than 0, then we have equality. And the theorem is proved. Yeah. Of course, I don't plan to ask the proof during exam. It was done just to show you how it works. Okay, thanks for your attention.